Hey guys, welcome back. We're going to go over the Bi-Variate data practice test. I kept it short with just 10 questions, so this shouldn't take too long. Make sure you actually do the practice test before you watch the solution video, otherwise it's not really going to help you out that much. Also, we are going to be taking the Bi-Variate data test in class next week. So if you're an A student, we'll do it on Tuesday. If you're a B student, we'll do it on Friday. And that will be the first test we've actually taken in person. So it's important you actually know how to do this, and you're not just like, I don't know, like watching this video while you're taking the test or something. So anyway, it's also going to replace your quiz score as well. So if you do better, that can help you if you didn't do as well on the regression quiz. So we'll also be taking our finals. I'm not sure exactly how or when we're doing finals or exemptions or anything like that. They still haven't told us. But we'll be doing that in person as well. So all the tests from here on out should be in person. We won't be doing take-home tests anymore. So it's important you guys actually know how to do this stuff. That's what I'm trying to say. All right, so number one, all but one of the statements below contains a mistake. Which one could be true? So we're talking about the correlation between two variables. So the correlation measures the strength of a linear association between two quantitative variables. So anytime we have anything that's going to be categorical, then we can't actually calculate we can't graph a scatter plot for it. We can't calculate the correlation either. Also, the correlation is a number strictly between -1 and +1. And -1 and +1 would be a perfect correlation, which never happens unless we're measuring some law of nature or law of physics, something like that. So you can kind of see what those kind of go from anywhere from a negative direction to a positive direction, and then in the middle there's just random. Also, correlation coefficient is calculated by the sum of the products of the z-scores, so that'll come in handy in just a second as well. All right, so part A says, or answer choice A says the correlation between the height and weight is 0.568 inches per pound. The issue with this one, of course, is highlighted in red, is the fact that correlation is unitless. It's based on z-scores, which is divided by standard deviations, so they no longer have their units associated with them. That's what allows us to compare apples to oranges and like z-scores from male athletes to female athletes to see who's the best overall tennis athlete or something like that. All right, correlation between weight and length of foot is 0.488. So the weight and the length of foot is both going to be quantitative data with their units, so we're fine. This is not beyond 1 for a magnitude, so this is actually the correct answer. It would be B. There's nothing wrong with this statement. Correlation between the breed of dog. The problem with breed of dog is that it's going to be categorical. So it's not like there's a range of breeds of dogs that's quantitative from anywhere from 0 to 100 or something like that. That's not how this works. Okay, correlation between gender and age is negative. Okay, that's fine. There's nothing wrong with that. There's no units associated with it. But the issue is with gender. So gender is not a scale or a spectrum. At least I don't think it is. I'm kind of confused these days. But anyway, it's going to be categorical as well, as far as I'm concerned. All right, so if the correlation between blood alcohol level and reaction time is 0.73, then the correlation between reaction time and blood alcohol level is going to be negative 0.73. The problem with this is actually the commutative property of multiplication. So if we switch the order of the z-scores, like the z-score of the x's and the z-scores of the y, that's not actually going to change the product or the sum of those products. It's like 2 times 1 is the same thing as 1 times 2, right? So if we switch the order, it's still going to have the exact same correlation. It doesn't become opposite just because we switch the order of the two. Now, whenever you calculate the slope of a regression line or something like that, and you switch the variables, you have to recalculate it, or you have to multiply it by the correlation squared or whatever when we're finding the slope in real units. But that's not what's going on here. So our answer would be B as in Bravo. Correlation of 0 between two quantitative variables means that we've done something wrong in our calculation of R. No. There's no association between the variables. That could be true. What's really going on is the correlation is measuring the strength of the linear association. So if it was linear and we got 0, then it would mean there was no association. But then it wouldn't be linear. So that actually doesn't work. I know it's really tricky, but there's no linear association between two variables. Yes, that is what it's telling us. The issue is because if we calculate the correlation coefficient of a parabola like this upside down, the positive values are going here, if you remember this. So our positive values are going, or positive products of z-scores are going to negate the negative ones over here. They're going to kind of balance each other out. So those are going to go to 0. And then the negative ones over here, negative ones over here are going to negate the positive ones that we have over here. Yeah, exactly. So when we take the sum of the products of those z-scores, it's going to actually be equal to 0. But that doesn't mean there's no association. It's just not a linear association. So you got to be careful. It doesn't mean there's no association between the two variables. It just means there's not a linear association between two variables. So the correct answer is going to be C. Re-expressing data will guarantee the linear association between the two. Whenever we have data that goes up and then down and changes direction like that, so it's not just curving like, I don't know, like a reciprocal or the square root or x squared, something like that. Those are different graphs, I suppose, whatever. You get the idea. It's not actually possible to re-express anything that goes up and down again. You actually have to fit it with a curve like a parabola or our quartic expressions or sinusoidal ones. So anyway, it's not possible to re-express this to make it linear. And so our correct answer is C as in Charlie. Residual plot is useful because it helps us to see whether a model is appropriate. Yes, so whenever we were looking at dive heart rates with penguins and their durations, it looked fairly linear, but the curvature was more clearly shown when we looked at the residuals. It's just more obvious. So that's one of the main benefits we have here. It might show a pattern in the data that was hard to see in the original scatter plot. That is true. That's very true. It's almost kind of saying the same thing. It'll clearly identify influential points. Okay, so influential points are points that, so a point has leverage if it is far away from the average x. That's not true, but influential points means that if we remove that point, it would greatly change the slope. And the problem with that is that they usually don't have high residuals if they were influential, because they drag the actual slope towards it. So that's not going to be true. So it's 1 and 2 only, so that would be C as in Charlie. Number 4, the correlation coefficient between the hours a person is awake during a 24-hour period and the hours the same person is asleep during a 24-hour period is most likely to be what? All right, well, you can only be awake or asleep for a total of 24 hours in a day. So let's say that you were awake all 24 hours. That meant that you were asleep for 0 of those, right? If you were awake for 12, you were asleep for 12, right? And then it just kind of trades off between the two. There's no state in between awake and asleep, I don't think. So there's no variation in those numbers either. So it's going to be a perfect correlation. It's kind of like a natural law or something like that. And it's going to be negative. So it's a trade-off. As one goes up, the other one goes down. So that's going to be exactly -1. When using a midterm exam scores to predict the student's final grade in the class, the student would prefer to have what? All right, so we're using the midterm to predict their final exams, or their final grade. So we'd rather have a higher than predicted final grade based on our midterm score. So with the residual plot, anything that's above the model, the line itself, which would be 0 in this case, is going to be more than what we expected. Anything that's a negative residual, that's below the line, is going to be less than we expected. If we're talking about your grades, we would want a positive residual because we would want it to be higher than what was predicted. So a positive residual because it means the student's final grade is higher than what we would predict with the model, which would be A as in alpha. Regression analysis of a student's college GPA and their high school GPAs found a coefficient of determination of 0.311, meaning 31.1% of the variation in the college GPAs can be accounted for by the model with the high school GPA. So we can remove 31% of the variation in the college GPAs, but there's still 68.9% of the variation left unaccounted for based on something else that's going on. All right, so high school GPA accounts for 31% of the college GPA. That's not a good way of putting it. Yeah, because we're actually referring to the percent of the variation, not the percent of the GPA. So it's close, but not quite. 31.1% of college GPAs can be correctly predicted with this model. No, remember, models are not perfect, and it actually would be incredibly rare to correctly predict a single value. We really just want to get it within a certain range of the actual values. That's where the margin of error is, but we haven't gotten into to that in part of statistics yet. So we don't expect any model to be perfect. All models are actually wrong because there's always going to be variation between the actual data itself and the model. It's just some models are useful if they're close enough, depending on how close they are. All right, 31.1% of the variation in college GPA can be accounted for by the model. That's exactly right. So it's 3 only. Correlation coefficient between high school GPA, was given to be 5 or 0.560 for a student with a high school GPA that's 2.5 standard deviations above the mean. What would we expect the student to have for a college GPA? Okay, so we're using regression to the mean essentially here. So we take our predicted, so our z-score for the x, which is the 2.5 here, multiplied by the correlation coefficient between the two, and that'll give us a predicted z-score for whatever we're looking for, which is the college GPA. So it'd be 0.56 times 2.5, which is going to give us 1.4. So we would have a positive 1.4, which is 1.4 standard deviations above the mean, would be our predicted value here. So our answer would be C as in Charlie. Graphically, what's going on here is however far we were able to deviate from the mean from our explanatory variable, the correlation coefficient times that value of 2.5 is how far we can confidently deviate from the mean with our response variable, which would be about 1.4. So the fact that this is always going to be backed up, regressing back towards the mean, the safest or the most conservative estimate would always be to just estimate the mean, which is just the average GPA, but we were able to deviate away from the mean because of the confidence that we have, because of the correlation between the two variables. So anyway, that's regression to the mean, the fact that we always regress back towards the mean with our predictions. All right, so the model, the square root of the distance. So do be careful, because notice we have the square root here. That's telling us that this is re-expressed data and it's not just the raw data that we would have starting out. So we do have re-expressed data here. It's given to be 3.3 plus something times speed, used to predict the stopping distance in feet for a car traveling at a specific speed in miles per hour. According to the model, how much distance will a car going 65 miles an hour need to stop? All right, so what we're going to do is plug in 65 miles per hour into the speed here, multiply it by this, add 3.3 to it, and that's going to give us a square root of the distance, which is 18.57. Now, that's one of the options for the answer choices, but that's not correct because that's the square root of the distance. So the last step that we have to do is actually to get rid of the square root by squaring both sides. So we're going to square the square root to get rid of it, give us back to the regular distance, which is going to be approximately 345 feet, which is D as in delta. All right, so on number 9, it asks if the point in the upper right-hand corner, which is going to be this point right up here, of the scatter plot is removed, what will happen to the correlation and the slope of the line of best fit? So the correlation here, if we remove this point here, so first I guess we'll look at the slope. All right, so if we remove this point right here, notice that the slope's not going to change, right? So all these points are pretty well balanced here, so the slope's going to remain the same. So this point is not influential because when we remove it, it doesn't actually change the slope, okay? So the slope B will remain the same, so it's going to be one of these. They're not both increasing or both decreasing, so we can go ahead and get rid of that. The next question we have is, did the correlation change? Well, the correlation is based on the sum of the products of the z-scores. So this point here, it's got a z-score that's really, really far away from the mean point. So if we drop the mean point down here, so this is our average x, okay? The average x, this value is so far away, maybe it's like 4 standard deviations away, and then from the average y is about 4 standard deviations as well. So the sum of the products of the z-scores is about 16. Now that's highly, highly unusual because remember, 2 standard deviations, we got 95% of data falling within 2 standard deviations. So it would be unusual even to have one that was a product of z-scores of like 2 and 2, like here. So this point 2 and 2. For the standardized stat plot, which would be 2 times 2 is 4. So having some of the products of z-scores 4 is unusual, but 16 is like astronomical. So if we remove this point, that's removing a very large product of the z-scores it's going to decrease the sum of the products of the z-scores. And so what's going to happen is our correlation is not going to be nearly as strong. So this point had leverage because it was very far away from the average x. It had a very large z-score for the x, but it did not actually have influence because it did not it did not change our slope, or increase or decrease our slope when we removed it, because it fell in line with all the other points. But it did increase our correlation coefficient, because without this point, it would not be nearly as strong of an association. So the correlation will decrease, but the slope will remain the same. So this would be E. And we would say that this point was an influential point. It was not, it had leverage, but it was not influential. That's how we'd explain that. So as a quick review of the difference between points with high leverage and points that are influential, points with high leverage have values that are very far away from the average x. So if the average x, the x bar was somewhere about right here, Bozo's shoes are very, very far away from the average x. Their x value here, whatever that value is going to be really, really far away. Okay, so that means that it had a high leverage because it has the potential to greatly change things, or maybe it won't, but it will. It has that potential. Okay, now if Bozo was a genius, then that would cause us to have a positive correlation just from that one point, even though there was really no correlation without it. If Bozo was a bozo, then again, because he had high leverage and also influence, he could greatly influence the actual slope as well. Okay, so basically, if we remove the point, so this point here it's really far away from the average of the x here. Okay, so if we remove that point, it is greatly going to change the correlation and the slope as well. So if I remove it, my correlation goes up because this was a negative value that was kind of holding it down. The other thing is that my slope with it would be a lot lower, but the slope would be increased a lot, and because it would follow the general trend of everything else if we remove this point. So this point we would say had influence because removing it greatly changed the slope. It had leverage because it was far away from the average values of x. So that's the difference between the two. So sometimes they overlap is what we're trying to get into. All right, so that's all I've got to say about that.